Greetings, mathematicians. Welcome to this next presentation on analytical geometry. Now we crank up the difficulty a notch or two by dealing with circles with the center not on the origin. So as you can imagine, not all circles are centered on the origin. They can be centered anywhere on the Cartesian plane. And those circles whose centers are not on the origin have a slightly different formula. For example, a circle with radius r and a center at the point P, which has coordinates of a and b, the equation for that circle, well, first of all, that's what the circle looks like. There it is, there's the circle. There is the center at point P, so not at the origin, it's off the origin. The equation for this circle will be that. It's x minus a stands for the x coordinate of the center. All of that is squared, plus y minus b. b is the y coordinate of the center. All of that is squared, and that is equal to the radius squared. So that there is the equation for a circle whose center is not at the origin. Again, it is an equation that would determine the coordinates for all the points that form the circumference of this circle. There we go. I've put a little green box around it, just for posterity. Now, the formula here, this one, is also derived from the distance formula, because if we wanted to work out the distance from the center to a point on the circumference, such as this point here, we would use the distance formula. There it is. We would substitute in our coordinates from the point on the circumference and the point at the center. However, we end up with this, because our x-coordinate at Q is x, our x-coordinate at the center is a, our y-coordinate at Q is y, and our y-coordinate at the center is b. So that is where the formula for the circle whose center is not at the origin comes from. Okay, so here's an example. Determine the equation of a circle with a center at 5 and -2 that has a radius of 8 units. So we start with the formula as usual. There it is, and we fill in what we know. Well, first of all, we know that the radius is 8, so 8 squared is 64, and then the a stands for the x-coordinate at the center, and the b stands for the y-coordinate at the center. Now you'll notice, because in our original equation we have a minus before the a and a minus before the b, in our final equation we end up with the values in the brackets having the opposite sign to what the coordinates of the center are. So the x-coordinate at the center is 5, in the bracket we've got -5. The y-coordinate at the center is -2, so in the bracket we've got +2. There we go. Simple as that. That is the equation of this circle. Here's example 2 then. Determine the equation of a circle with a center of -3 and 4 that passes through the point 2 and 7. Well, we start again with our formula. Then we fill in what we know. We know the coordinates, the x and y coordinate of the center. There we are. So we fill those in. There it is. Again, the coordinate in the bracket, well, the number in the bracket has the opposite sign to the coordinate of the center. So it's -3 is the x coordinate of the center. So it's +3 in the brackets. And +4 is the y coordinate at the center. So it's -4 in the brackets. Now we need to somehow work out what the radius is. Well, that's not too difficult, because we have another point here, and we can substitute these coordinates in place of the x and y in the equation, and by doing that we will be able to work out the r. There we go, so we substitute them in, now do some calculations, and we end up with this. Now again, we don't have to square root the 34, because the equation calls for r squared. So we know that r squared is 34, so the equation for the circle is this. There we go. Done. Example number 3. Determine the coordinates of the center of the circle with the equation that. So this is pretty straightforward. All we need is the coordinates of the center of the circle. This comes from the x-coordinate. That comes from the y-coordinate. All we need to do is change the signs. And there are the coordinates of the center. Well, that was easy. Here's example 4. A circle has an equation of this, And we need to determine the coordinates of the center of the circle and then determine the radius of that circle. Well, you will notice the equation that we are given is not in standard form. It is all mixed up. The standard form looks like this: bracket squared plus bracket squared equals a number. Here we don't even have any brackets. So what we're going to have to do, first of all, is to complete the square for both the x part and the y part. If you don't remember completing the square, you're going to have to go back to grade 11 algebra. But we're going to complete the square for the x part and the y part. So there's our equation as it stood. What you'll see I've done is actually, no, you won't see I've done anything because I haven't done anything yet. I'm going to do something now. Now what you'll see I've done is I've moved the 14 just to get it out of the way of the completing of the square. I've moved the 14 to the other side so it becomes negative 14. Now, if you look at the x part, what number do I need to add here to create a perfect square trinomial? Well, if you remember the method, I halve this number and then square it. So half of 4 is 2, 2 squared is 4. There we go. And here, I need to think what number must I put there to create a perfect square trinomial for the y's. Again, I halve the 10 and square it. Half of 10 is 5, squared is 25. So I need to add a 4 here to complete the square for the x's. I need to add a 25 here to complete the square for the y's. Because I've added a 4 and a 25 on the left, I must also add a 4 and a 25 on the right. So I end up with this. Now I need to factorize each trinomial. I factorize the x trinomial and the y trinomial separately, and I get that. And there is my equation in standard form. Now that it's in standard form, it's easy to determine the coordinates of the center of the circle. I just read them off the equation. These two numbers, that's the x coordinate, that's the y coordinate. Just change the signs and le voila, as they say overseas. They probably don't say it like that, but that's my impression. Now, question B, we need to determine the radius of the circle. Well, again, it's easy. This number here is the radius squared. So all we have to do is square root it. Oh, wait, I'm waiting for the red box. Red box complete. Now we can move on to the radius. There it is. So that number there is the radius squared. So all I have to do to find out the radius is square root it. So it's root 15 or 3,87 and some change. And that is the answer. It's a shock. Example number 5. Determine the coordinates of the points of intersection of the circles described by the following equations. What? So I've got two circles and they are overlapping each other. And I need to find the points of intersection. So, as with other functions, if you want to find the point of intersection between two lines or two graphs, you have to make the equations equal to each other. So we're going to do the same here, but we'll need to multiply out the two equations before we can make one equal to 0. What? What am I even saying? Let's try that again. We are going to do the same thing here. I'll read along with my arrow. We are going to do the same thing here, but we'll need to multiply out the two equations and make each one equal to 0 before E can proceed. E by gum. From Yorkshire now, am I? Aye. Right, so I take this one, I'm multiplying it out, and then getting everything over to the left to make it equal to 0. Then there's a vertical line, a glorious vertical line. Now I take this one, multiply it out, get everything onto the same side, and a 0 on the other. Now you'll notice this equation is equal to 0, that equation is equal to 0, so the left-hand side here and the left-hand side there are both equal to the same thing. So I can make them equal to each other. Now if I simplify this, you'll find this x squared and that x squared cancel out, that y squared and that y squared cancel out, so that gets rid of the squareds, and we're left with that. Now I can divide everything by 26, and I'm left with that. Now I can get the x by itself and everything else on the right-hand side, and that will be equation 1, because we're now going to do some simultaneous equations. I'm going to substitute this back into either one of these equations. I could either do this one or that one, doesn't matter. I've chosen to do this one. So I'm going to substitute equation 1 in place of the x here and here. I get that. and then multiply it out, I get this, then simplify, I get that, then divide everything by 2, I get that, then factorize, I get this, and then that means my y equals 5 or -1. Now we're getting 2 answers here, and that makes sense because if I have 2 circles overlapping, you can expect them to be overlapping in 2 places. So I need to have 2 sets of coordinates. Now what I need to do is substitute these y coordinates back into equation 1 to work out what the x coordinates are. There we go, and there we go. So the coordinates of the point of intersection are as follows. 2 sets of coordinates because they're 2 places where the circles overlap. Well, there's the red box of glory. Ah! Now, it makes sense to have 2 sets of coordinates because when circles overlap, they cross in 2 places. There's an example. See, it crosses there and there, 2 places. I broke my leg in 2 places. The doctor said I should stay away from those 2 places. Oh, shock! Now, interactions between circles. There are 4 types of interactions between circles that we need to consider right now. I'm not saying there are only 4 types in the world, but these are the 4 we're going to concern ourselves with at the moment. Firstly, if 2 adjacent circles just touch so that they only make contact in one place, we say the circles touch externally. There we go. Sorry, I'll try to be more mature. These circles are touching externally. Right, if 2 circles touch externally, then the sum of their radii will be, exactly equal to the distance between their centers. So, if the radius of the left-hand circle is that, and the radius of the right-hand circle is that, if they are touching externally, the distance between their centers will be exactly the same as this radius plus that radius. Aha! There it is in mathematical notation. Now, another type of interaction is if the 2 circles touch at one point, but one circle is inside the other circle, we say the circles touch internally. There we go. There are 2 circles touching internally. Now, if the circles are touching internally, then the distance between their centers will be equal to the difference of their radii. So the distance from this center to that center will be equal to this radius here, the big radius, minus the little radius. There we go. So that's the distance between the 2 centers, and it's equal to the long radius minus the short radius. There it is in mathematical notation. The third type, if circles overlap, like we had in our previous example, like this, then the distance between their radii, the distance between their centers will be bigger than the difference of their radii, but less than the sum of their radii. So this distance between their centers will be bigger than the difference of their radii, but less than the sum of their radii. There we go. Finally, it's possible to have 2 circles that don't overlap at all. There we go. 2 unoverlapping circles, completely separate and distinct. Those circles are on lockdown. They are experiencing social distancing. Now, if 2 circles do not overlap at all, then the sum of their radii will be less than the distance between their centers. This radius plus that radius will be less than the distance between the 2 circles' centers. There we go. There it is in mathematical notation. Oh, shock! Now, example number 6. We need to determine whether the circles defined by the following equations touch internally, externally, or if they overlap or nothing at all. So, what we have to say here, first, what do we have to do? First, we must determine the coordinates of the centers. That's easy enough. We can just read it straight off the equations. There we go. There are the coordinates of the centers. This is the center of this one. This is the center of that one. Then we need to use the distance formula to find the distance between the 2 centers. There's the distance formula. Plug in the coordinates, the x and the x, the y and the y. And there's my distance. The distance between these 2 centers is 3 units. Now I need to work out the radii of the 2 circles and then calculate the sum and the difference of these radii. So, the radius of this one, to work out the radius, I take that number and square root it. There it is. To work out the other radius, I take that number and square root it. So the radius of the one circle is 4 units. The radius of the other circle is 3 units. So the sum of their radii is 7, and the difference of their radii is 1. So what can we conclude about these two circles? Do they touch internally, externally? Do they overlap, or do they not touch at all? Well, this distance is bigger than the difference, but it is less than the sum of the radii. So that means the circles overlap, because this distance is the difference between the radii, but it is less than the sum of the radii. So those circles overlap. Well, that's all I've got to say about that. Okay, bye-bye.